be explaining how to design an SR flip-flop counter. Now our objective here is to create a binary counter which loops through the sequence 3, 2, 1, as I've labeled here, with the binary numbers for each of the respective decimal numbers. And way I can see here, we have this 0 here, which represents our special case, which if we run into it will put us back at the start, which is 3. Now our methodology of going to approach this problem will be to find the number of flip-flops we need, make our SR flip-flop table. We will use that SR flip-flop table to make our excitation table for our counter, and then finally we will get our flip-flop equations from our K-maps. Now, what we can do to find the number of flip-flops is we can either look at the number of bits that we're dealing with, which is 2, and that will directly tell us how many flip-flops that we have. So we could say that since we have 2, we're dealing with 2 bits, we will have 2 flip-flops. Another way we could do this is we can look at the equation 2 to the power of n is greater than or equal to our total states. So n, we can see here, is going to be the number of flip-flops that we have. So we can see that 2 satisfies this equation, and it has to be the smallest number n. So we can see here that 2 satisfies this equation, which means that we'll be dealing with 2 flip-flops. Either way works. Now, what we can do here is we can look at the SR table here. Now, to build this SR table, which we'll be using for our counter excitation table, we will look at the current and next states that we can have. So we can first of all, we can start with a 0 and go to a 0. Now, there's 2 ways that this can happen. Either this means that we started with a reset, either we had a reset signal that was sent, or nothing happened. So to mark this for our SR value, what we could do is we can mark a 0 for S, because 0 is constant throughout both of these, but for R we can see it could be a 0 or a 1. So we put an X here to mark that we don't care what R is. Now if we start with a 0 and our next state is a 1, what we do here is we can see that the only way we can get this is if we send a set signal. So that means that our SR value here will be a 1, 0. If we start with a 1 on the other hand, and we have a 0 as our next state, this means that we sent a reset value. So that means that SR will be 0, 1, and if we start with a 1 and end with a 1, that means that either we sent a set signal or we did not change anything. So that means that we put an X for S because S can be a 1 or a 0, and we put a 0 for R because it has to be 0. Now using this table for SR flip-flops that we've just built, we can go ahead and create our excitation table for our counter. Now what we do here is we're going to create a flip-flop. We're going to create a flip-flop input for SA and RA and for SB and RB. Now I've marked the red numbers will be representing the changes in A, and the blue numbers will be representing the changes in B. So first we're just going to look at SA and RA. So if we look at the red, we can see it goes from a 1 to a 1 in the next state. Now we can see the 1 to a 1 from our table here will result in an X0, a do not care 0. So we are at do not care 0 here, and our next state will be, our next present state will be 1, 0, or be 1, 0 here, and we can see here that results in 0, 1. Our next state here, we have a 0, and then goes to a 1, and that will result in a 1, 0, as I put here, and then we can either have a 0, 1, which will also result in a 1, 0. Same goes for B. So if we go ahead and look at the blue numbers here, we can see this 1 changes from a 1 to a 0, and that means that we get a 0, 1 SR output. And then here we have a 0, 1, which will result in a 1, 0 SR output. A 1, 1 will result in a do not care 0 output, and then a 0, 1 will result in a 1, 0 output here. Now, what we'll do is we'll build our K-maps now for our states. So now what we'll do is we'll create our K-map for SA and RA, and then for SB and RB, giving us 4 total K-maps and 4 total equations. Now, what we could do here is we just look at our present states, and we're going to use that to fill out the K-map. So we look at 1, 1, that's going to give us an x. 1, 1, we fill in an x here. 1, 0, it's going to give us a 0 for SA. And we have a 0 here. 0, 1 will give us a 1. 0, 1 will give us a 1. And 0, 0 will give us a 1. So we can see that we could group these two ones together, which will give us A as, not A as our equation for the SA flip-flop. Now for RA, what we do is the same exact thing. We look at the table here, so we have 1, 1, and we can see here for RA we get a 0. So for 1, 1 we put 0. For 1, 0 as our present state, we go to a 1. So 1, 0, give it a 1 here. And we have 0, 1 as our present state, we get a 0. And we have 0, 0, we get a 0. So we fill in the rest of these slots of zeros. And since 1 is only filled in the spot that lines up with A and not B, that means our equation for this is A, not B. Now we're going to go ahead and look at SB and RB. So what we could do here is the same exact thing we did before, except with SB and RB. So we have our present state as 1, 1. That will give us a flip-flop input of 0 for SB. So for 1, 1, we're going to put a 0. If we have a 1, 0, we're going to get a 1. So 1, 0, we're going to get a 1. If we have a, let's see, a 0, 1, 0, 1, we're going to get an X. And if we have a 0, 0, we're going to get a 1. So 0, 0, we put a 1 here. And we can see that this lines up for, develop the entire column of not B. So that means not B will be our equation here. Finally, we're going to look at RB. And we can see for RB that we have 1, 1 will give us a 1. So 1, 1, we put a 1 here. For 1, 0, we will get a 0. For 0, 1, we'll get a 0. And for 0, 0, we'll get a 0. So we fill in the rest of these slots with zeros. So since AB is the only cell that is filled in here for the 1, we will say that our equation for RB is AB. And if we combine all of these equations together, we can get these 4 equations, which are not A not B, not B, and AB. And that is how we can create a counter using SR flip-flops. Thank you very much.